All right. Hey, everybody. This is Jim Shaw from Fastway Engineering. Thank you to Kara and Kevin and Zaina for kicking us off here. And I'm going to continue the conversation around some of the design and simulation tools that we use for additives, of course, specifically for metal additives. So for the next couple minutes, we'll start off with a little bit of a discussion on the landscape of the tool sets that are available, and then digging in specifically around some of the DFAM or design for additive tools. We've got a couple case studies, to share. Always good to see these tools in action and where they've helped, companies, people, engineers, production save money, time, add value, et cetera. And then at the end, we've got a couple minutes to do something that I'm really, really excited for, which is a live demo. And I want to show you guys the sort of steps that we go through to simulate the additive process when we've got a directed energy deposition model to show you. I think that there's a common misconception that these simulations are incredibly difficult and take a really long time to learn and do well. And hopefully today, what I can show you is, maybe it's not as hard as you think it is, and maybe it is something that's attainable. And so I'll walk you through sort of, what a simulation looks like. It's just a big fancy calculator, and we'll be able to walk through what we need to put into it to see if we get some reliable results. But simulation is really just a part of the category of design and simulation software. In a nutshell, additive manufacturing is a digital to analog conversion, right? So up until the point of actually getting, some metal being deposited onto the build plate, we really live in a very, if not solely, digital process. And that includes a variety of software that are being developed today, brand new for this application. And simulation in particular is critical. Why? Of course, I live in the simulation world, so I look through, production through that lens, through product development with the simulation lens. But, if there's anything that we can do to predict potential quality issues or predict the amount of money we're going to make on a run, then let's do it. And the fact that our design and preparation for production process is purely digital, then simulation becomes a key part of that, because we have the design, we have the geometry, we have the CAD, we have the slicer, we have all the things. We can even simulate the actual print, which we'll see later. And so we live in what I think to be the most exciting time, because we are seeing this intersection of the continuation of our design and CAD and FEA and CFD, our simulation tools, with additive manufacturing in metal. So it's a really, really exciting time. I am particularly excited about it because we've got some tools that have been around for quite a long time, and we've got some new tools. So I've got this big list here. My colleague Alex allowed us to use this for the class today. But what's really, really interesting here is you'll see, at the top, we have a lot of software companies that I am sure you're familiar with. I'm sure we've all heard of some of the big five or the big 10, whatever you want to call it, some of the large CAD companies that have been around for decades, and simulation companies on there, right? So Altair and Ansys. And then, of course, digital manufacturing, additive manufacturing isn't in a vacuum. If there's one example of a technology or a process or a capability that touches every single part of the business, then it's additive, right? So we've got our CAD or our PLM, product lifecycle management solutions. We've got our ERP system, right? Time tracking, cost of goods sold tracking, and then this awesome, fun section in the middle of the graph, what we call the challengers, right? The new ones, the startups, the exciting companies that are haven't been around for decades, but are redefining and disrupting the industry with respect to new tools, new ways of looking at things, and of course that doesn't happen all by itself. And so we've got new players also in the supply chain management, quality control, and manufacturing and PLM tool. So this is a really, really fun space to be in. I guarantee you that if we were to show this screenshot, even in 6 months, we would see more players, and we would probably see some, mergers and acquisitions and things like that. But in the meantime, if you are in a position to be vetting new tools, then maybe this list gives you a good starting point, because we know that can be pretty intimidating to try to create a new tool set. The landscape of software, we kind of categorize it here in about 6 categories, right? So 6 different sort of sub-disciplines. So the first one will be design for additive. And, some of the sort of key terms or technologies or software you might have heard of is generative design or topology optimization. We see a great example here in this upper left-hand corner of innovative shapes, organic geometry, things that really a human would have a very difficult time coming up with. But really, it's an algorithm, right? It's a piece of software that just takes in some of the requirements that could be design requirements, could be cost requirements, et cetera, and shows you the most optimum geometry. And these tools are new because although we've kind of had some optimization tools for a while, and as a design engineer, I won't call myself a design optimist, but now that additive allows us to manufacture geometry with a lot less restrictions and limitations, we have, say this optimized topology design for this bracket we see here that is actually manufacturable, right? We can't CNC machine that. It'd be very, very difficult to say plastic injection mold that forge or casting, right? Unless we were to try to abide by some of the draft angles and parting lines, et cetera. So build setup is a category, right? So how do we design the actual structure for some of the technologies we need to have a structure, orientation, et cetera? How do we reduce residual stresses? The actual process simulation itself, which is really understanding the temperature profile and the residual stresses and strains and deformations, all the things that, we want a part to come out of that machine in spec. Are there ways for us to simulate that process and predict, is it going to be in spec or not? And if it's not going to be in spec, can we pre-distort that? And the answer is yes. Material analysis, so micro to nano, if you will, analysis, which Zaina just went through quite a bit of detail on that. So we've got a whole host of tools to kind of validate, verify, and compare against some of the physical testing that we need to do. And of course, as I mentioned before, the connection to data management, material property databases, testing, qualification, validation. So these are the 6 kind of major categories that we put some of the design and simulation software into. Today, what I'm going to go through are the 2 of the top 3. So we're going to talk about DFAM here, starting on the next slide. And then, as I mentioned, we'll have a process simulation. So we just don't have time to go through all 6 today, unfortunately. So to kind of understand the value that some of the new DFAM softwares bring to the table, we sort of have to start with looking at what's wrong or what are the limitations of today's design process, right? So, currently, I'm sure all of you have been a part of this process in one way or another. I've worn a design engineer hat for quite a few years. So, I start on the far left-hand side here. And my job might be to take some sort of requirement, some functional aspect of the challenge and say, give us some geometry, right? Jump in the CAD tool, give us some geometry, make a bracket, make a part, and tell us, show us that it's going to work. And so we'll analyze that, right? And so we're constantly going back and forth in today's sort of hardware product development process with CAD over to simulation, back to CAD, back to simulation. We're optimizing geometry. We're redesigning. We're trying to do as much of this in the computer so we don't have to spend too much money on prototyping and testing and getting it wrong and doing it the physical way. But then once we're done with a design that we think is awesome, we send it over across the wall, if you will, to production. We do what we call DFM or DFA, design for manufacturing, design for assembly, and then we'll get more feedback. We'll go back to CAD, we'll redesign things, reduce the number of parts, try to have a, commonized hardware. Can I install everything from above? Some of the methodologies that we've developed over the years. But what I end up doing is going back into CAD, right? And then when we're done with that, we go to the CFO or the finance team or the buyers, and we say, here's the cost of the design, and they say, well, that's not going to work. We need to take 25% of the cost out. Well, back to the drawing board, back into CAD. And then we go to production, and then we learn something, right? The first time we run production, we learn something that could be better. we ECO it, right? We issue an engineering change order, back to back and forth. And so, what we started off with, years ago is this more serial process. And what we found out was it takes a long time, right? And we're always getting pressure to try to squeeze this process down as quickly as possible. And so what additive allows us to do is take those requirements. So function, DFM, DFA, cost, assembly, and putting that in parallel, right? So, what if we could? What's the dream? Well, the dream is, can I take those requirements instead of waiting to do each one in serial, go back to the CAD drawing board, if you will, can we somehow put those in parallel, right? We've been talking about this. You might have heard the term shift left, if you will, meaning we shift our requirements of the process all the way to the left. Before I start creating geometry, can I have cost, function, printing, printing in the case of additive, can I have all that taken into account? And the answer is yes, particularly because since up until you're actually depositing material, depositing metal onto the build plate, you're strictly in ones and zeros. We're strictly in the computer. So why not develop a software that can take those requirements and take them into account and optimize that in parallel? And that's what we have today, right? We've got these sort of algorithms, if you will, topology optimization and generative design that include some of the requirements for manufacturing, especially since we have different processes, right? So we have powder bed fusion, we have DED. Those have particular requirements as well with respect to the machine, the speeds, and those are all incorporated now into our DFAM tools. What we're doing by shifting all of those requirements further left and putting it into the software is basically developing optimized geometry, optimized designs that have met all of the hard requirements from the computer to the people to the floor, simulation, stress analysis, fluid dynamics, and developing, again, geometry that's so advanced, right? So optimized that, our traditional CAD tools can't do this. Extrude, revolve, loft. Throw those out the window, right? What we're talking about is a brand new philosophy, a new approach, right? And so DFAM is really an optimization process. The geometry you see on the screen here is 100% developed by a computer. Sure, we sat there as humans and entered in sort of the requirements, minimum wall thickness, maybe some sort of overhang geometry or something, maybe a minimum support, some control of deformation. But what we're creating is geometry specifically for additive manufacturing. And, we say that we, quote, get complexity for free. And although nothing's free in engineering, design, and manufacturing, the complexity here didn't take any additional time. So it's free with respect to that level of effort and the time it takes for a designer to generate this. And one of the key things that we're doing too is we're combining all of these, parts, right? So we'll have an assembly of 30, 40, 50 parts. Steel hardware, aluminum brackets, maybe some other alloy to withstand some sort of heat or some sort of stress or fatigue. And we say, listen, what if we could take all these 50 parts, whatever, put them into one part? What does that geometry look like? Which alloy would we need, right? So Zena just got done walking through, the material aspect. We are going to change the material. If you're going to take a design of a part or an assembly and prepare it or redesign it for additive, you're going to change the alloy, right? The alloys we have for additive are different because they have to withstand this phase change and the particular process, powder bed fusion, whether we're melting it or we're starting with a powder, et cetera. So, we really have a white space, a brand new way of looking at things, and the opportunity is unbelievable. And I'll give you an example. So here we have a small sort of nano satellite, also known as a CubeSat. This is called a 3U CubeSat. So you'll notice that it's 3 units tall and then 1 unit by 1 unit in cross section. And this particular nanosat will get launched into space, live up there for a year and a half before it comes back down and burns up. But in the meantime, it's going to take some really awesome pictures of stars and clouds and weather and et cetera. Well, it's really expensive to launch the CubeSat, launch anything, right? And so every time we launch something, the price that we pay, the cost of it, is actually really is very directly related to the mass, right? We have to launch this thing, get it out of our atmosphere, and so every kilogram, every pound that we add to our brackets is going to cost us more money, more fuel, more space in the rocket that goes up. So the challenge we see in front of us here is we've got this really stiff bracket. It needs to hold the optical camera here as sturdy as possible so the images aren't blurry, but we need to reduce the mass by a lot. In fact, the challenge that was given here was we reduce the mass by 91%. So basically taking out an entire kilogram out, which is just a couple pounds, right? But this is quite a small thing. And so we're going to compare a couple of approaches. And what I'm going to do here is compare sort of our baseline block, right? A big gigantic block of 61 T6 aluminum with a traditional CNC process. And yes, I created that quote unquote CNC part. So, feel free to judge me on that shape there, but I try to keep it relatively simple and relatively machinable for a 3-axis or even a 2.5-axis CNC machine. And then compared that to 2 additive metal processes. One is topology optimization, which is this algorithm-based software which can, for a given shape, basically remove material in the most efficient way, provide this beautifully organic and efficient geometry that can be printed, versus a slightly different approach, which is a lattice infill. And there's a variety of different lattices that are being engineered nowadays to satisfy a lot of these structural requirements. And so what we're going to compare here is, first on this row, we're going to compare the mass. So our original mass was 1.15 kilograms. And you can see that using our software, using our CAD tools here, we're going to enforce, we have to get that mass down to 0.1 kilograms. And so you can see we successfully did that. So for the traditional CNC approach, the top opt approach, and the lattice design, we did meet our mass goal. Now, the other goal that we have is to maximize what we call the resonant frequency, or the frequency at which this structure will vibrate, were it to withstand some sort of vibration and shock. And these brackets, anything that gets launched, the harshest environment structurally that it's going to experience is leaving our atmosphere, right? We've got, I don't know, tens of Gs, let's say. We're at thousands and thousands of miles an hour. We've got this, all kinds of vibrations coming from the rocket. And so our original, and so that number, for those who aren't familiar, that number has to be as high as possible. So our baseline had a pretty high resonant frequency, almost 4,000, almost 4 kilohertz there. So at 3,742. And using a human in a traditional CNC CAD environment, not bad. 2,000, I guess. Lattice, not so much. So this particular lattice was only able to get 1,500 hertz as its resonant frequency. The topology optimized design. The topology optimized design is almost as good as the original design. And again, that is not a shape that, and I mean, there's CAD designers in the audience. I'm not saying you can't do this. I'm saying the chances of you coming up with this organic shape and this optimized geometry is pretty low. It's not zero. I think we might have a couple of experts in the audience, but ultimately we can leave this up to the software, right? The software is going to be trying hundreds, if not thousands, of different options, and then provide us with the best one. So, and again, we could have been doing this 10, 20, 30 years ago, but what it creates is geometry that is not manufacturable by any other way. And so now with this combination of this DFAM, top opt, and additive, we're developing parts that are lighter than ever before and stiffer than ever before. It really is facilitating this private space race, this fun aerospace renaissance that we're going through. To continue the case study here in aerospace, here's an example from Croft Filters from Ansys, where one of the things we need to think about is when this filter, for example, a lot of filters, heat exchangers, another great example. We've got a lot of thin walls. We've got a lot of open air, if you will, or open space in a design to allow a fluid, gas, liquid, whatever. And one of the challenges there is, as the part gets printed, it's actually going to deform. And so by doing a full simulation, a full process simulation, we're able to predict that deformation or that distortion, if you will. And then if we take that one step further and say, hey, if I can predict in this case on the left-hand side underneath that left red circle, you'll see that the part grew. It kind of expanded a little bit, and then it shrunk again. And so, there is maybe a cylindricity or some diameter spec that we weren't able to meet on the first print. If we're able to predict that and then take that and sort of redistort the geometry, then as it prints, it should cool, distort, and distort into spec. And that's what we see on the right-hand side. So on the right-hand side, by doing a full process simulation, in this case in Ansys, we're able to predict the distortion, modify or pre-distort the geometry, and then what we get is the net geometry. Really what we want, we don't want to have to post-machine. We don't have to do anything. We really don't want to iterate too much. I mean, this is still not a cheap process per se. We're getting cheaper every day, but, we don't want to have to throw parts away. By predicting that shrink, by predicting the expansion, we can shrink the CAD model and we can print it exactly as it comes out of the machine. We pull it off the bed and it hits the part, hits the spec. So that's the really, really cool stuff that we're doing. And the third case study that I want to show you guys here is, we're able to take a huge amount of parts. And again, a lot of the case studies that we have right now are coming from aerospace, coming from, these really expensive, really long lead item type applications, and showing, sort of the commercial world what we can do. So a lot of case studies you'll find are from aerospace. And here's another great one that we have from Ansys, which is, there's this massive rocket injector, right? And I think this part originally had, I probably think it had like 40 or 45 parts in it. And they all have to be pretty precise, right? I mean, this is a rocket injector. It can't really go wrong. It needs to get fuel from a storage tank into the combustion chamber. This particular part, so many manufacturing challenges were solved just by going to additive. Now, it wasn't the alloy that saved the world, right? It wasn't the machine that made everyone look like legends. It really was a combination of technologies, processes, redesigns. And so what happened? Single part. You could not make that geometry in a single part by doing it any other way. You just can't machine or forge or cast or really get into some of the small details on the inside. Reduce the number, and these are things that maybe engineers don't think about. Reduce the quantity of purchase orders from a supplier. If you're watching right now, you're probably related maybe a little bit more to the production floor than you may be from design engineering. If so, you're familiar with the paperwork, the painful paperwork that can be a huge bottleneck. Inventory costs and transportation costs. Think about having 40 suppliers versus having one, okay? How many trucks have to move? How much fuel has to get burned, okay? And if you have to pre-purchase parts in a certain quantity and they have to sit on a shelf because your machine shop supplier says the minimum's 50 and you're selling 30 a year. Well, you're buying 2 years worth. It's going to sit on the shelf, collect dust. That's not free, right? Labor, because instead of installing 40 or 50 different parts together, we only have to put one part into the machine wherever it goes, and then we have that many less parts that we have to inspect. Right? We now have to inspect one part, and we might have some minimal, critical dimension that we might inspect. We're not going to inspect every single dimension on that part, but we're going to be able to find out what the critical dimensions are, inspect those, maybe automate that. But we certainly don't have to inspect 40 parts. Again, there's a huge cost associated to all these different aspects of the supply chain that maybe a design engineer may not have at the front of their lobe as they're sitting there in their CAD program. But ultimately, the value proposition here, right? The business case, as we say, is when companies are looking at metal additive and looking at bringing it to their process, okay, it requires a one-time investment engineering effort. For any given project, right? Engineers or an engineer is going to sit at their CAD station and say, how do I redesign this part? How do I minimize the distortion? How do I reduce the number of parts? DFM, DFA, DFAM, minimize post-processing, and all you have to do is calculate what's that one-time investment versus all of these other costs that we can reduce. It's pretty simple ROI. When's the payback? And so that is what we're talking about today, right? That's what Kevin and Kara and Zane and I are talking about, is how do we get people in the audience to start to re-look at things with a different lens, re-look at this, look at new tools, look at new processes, and is it worth it for your business to execute a one-time investment engineering effort and get that payback, because the payback's going to keep coming back again and again. And this is a great example here in this rocket injector. So now I'm going to turn on these animations here. If I can get them to start, I'll try to start these in order all at once. Okay, so how do we predict distortion? How do we compensate for that? And so as we get prepared for the demo here, what I want to just kind of highlight for those who are new to the simulation side of things, what we're talking about is actually simulating the printing process. The printing process can either be done layer by layer by layer, like a powder bed diffusion, where each layer of material is added very, very quickly relative to the overall print, or a directed energy deposition, AKA sort of a fancy welding process, right? Where we're adding material maybe a slightly slower rate on any given layer relative to the overall print time. This is an animation of a powder bed fusion process. We have some sort of a blade here, right? Some turbine blade. And one of the challenges with turbine blades is you start off with a big hunk of metal and you have to remove at least half of it. You've got all these chips on the floor. We've developed these, incredibly automated 5, 6, whatever axis machines to try to create this amazing shape, this optimized turbine. But additive is a really, really, really good solution here, because we can get to really close to that net shape, and then all we have to do is go back and maybe do a single pass or a double pass on a CNC to get the surface finish we need for fatigue. But what do we do when we simulate this process to make sure that we get the closest part out of the printer with minimized distortion? Well, we're coupling some of the physics, and Zaina already walked through some of the material properties that we need, and so those material properties, the alloy, the material decision goes into our software, and we are executing what we call a fully coupled thermal stress model. Okay, so there's a finite element model. This has a temperature versus time profile. So on the far left-hand side, you can see that we've got this transient thermal analysis, and we're actually looking at the melt pool temperature. So the simulation here is every row will get added at the melt pool temperature. We're assuming that it has already been solidified. So this is not, you might have seen online some of the fancy sort of, this is liquid and then it transitions over to solid. Well, in this case, everything's solid line by line being added at the melt temperature, and then we're cooling it, right? As we print at that temperature, we're putting a lot of energy in, whether it's an extruded process or a laser-based process. A lot of energy is heat. And then the heat has to get dissipated. It'll conduct down into the part. It will convect out into the gas or the air that's inside the print machine. So capturing that thermal profile is really critical to capturing the stress and deformation. So in the middle, you'll see the deformation. So what we're able to do using the coefficient of thermal expansion, as Zaina had mentioned previously, is we're able to find out that as this thing cools, what is that deformation, right? Parts that heat up, they expand. As they cool, they shrink. So how is it going to shrink, and how is the part in each layer going to get constrained as it shrinks? And then on the right-hand side, of course, there is a residual stress or strain, right? So as we continue to add hot layers, the layers underneath are going to get constrained more and more. They're going to want to shrink, and they can't. And so as they try to shrink and can't, we get these stresses. And what's really important to know is, one of the questions we have to ask ourselves is, are we going to heat treat? Are we going to post-process? We already have to machine this particular blade to get the surface finish we want, but it's just a little bit of material. But if we have a little bit of residual stress from the printing process, we want to know about it. And then we can either make the assessment of, is that stress going to stay there, or do we need to relieve it with some sort of post-processing heat treat? So that's what the technology, that's the physics of the situation. And now I'm going to swap over to Ansys and show you how one gets set up. I've got a pre-built one here. And for the record, I am going to show you a directed energy deposition process. So we are going to see some of the layers get added. This this is another example of a DED process. And as you can see, because of how I'll say slowly the material is added with respect to the total print time, in this case, you'll see what we call these sort of chunks or clusters of material being added. And so all of that can be controlled. And I know it sounds like a lot of detailed information that might be kind of intimidating, but on the left-hand side, these are some of the inputs, right? This is a thermal structural model. So we have to know some of the thermal aspects, and some of the material properties are documented out there online, and some of them we have to talk to our supplier about. And the other thermal aspects of this model are just part of the process, right? As we're trying to drive up the speed, drive down the print time, and basically control the quality. So a lot of that is really us, on the machine printing side, dialing in. So let me move over to Ansys for a second. So for those who haven't seen Ansys before, this is our Ansys workbench. And Ansys workbench is kind of like a flow chart, right? Sort of a physical flow chart. And all it's showing us right now is that we're flowing, if you will, some initial geometry, which is our print geometry, into a thermal analysis. And that thermal analysis is going to get executed and then coupled with our structural analysis. So I'm just trying to show you guys that, these tools are really built to be very visual and help us understand exactly what we're trying to do. And as I move into the actual model here, you'll see that it looks a lot like a CAD tool for those who are brand new to Ansys Mechanical. And what we've got is we've got a geometry. I'm just going to show it before we get into the physics side of things. But we've got a geometry we call our staircase. And the staircase here is just meant to kind of step up and step down and step up and step down. And it's really pushing the limits of the geometry, but it's a great use case for testing out the parameters of the machine and tuning our model, right? So these models are not 100% accurate right out of the box. You can't just guess a bunch of numbers or predict a few things, type them in, and then hit go and get the answer that's right. A lot of times, and particularly in additive, what we're doing is building a model, making our best guesses, printing apart, finding out how close we are, and then tuning it. And so all of these models have a built-in sort of tunability to it because it's so important. So, you're never, well, I should say never, but it's very rare to get the absolute first print out perfect. But certainly after a few prints, you can dial in this process, and then after that, you can predict it, and there's a lot less waste. So what we're doing is bringing in the geometry from any CAD tool. You can see on the top left here, we're entering in our material properties. So in this case, we're just using the 316 stainless. We have a whole host of other materials. Zane had mentioned a couple before. Copper, of course, is new and exciting for us. And then we have to do a process that we call meshing, which is just taking our geometry and breaking it down to small blocks. That allows us to analyze the physics in small blocks and print those small blocks layer by layer. So in some cases, you can see they kind of represent how material is being added to the part layer by layer. And then in our tool here, we have build settings. And so these build settings on the left, these are all the settings that we need to put in. They're characteristics of the geometry, characteristics of the print, that what comes out of the slicer, the G code, and the environment of the machine. In fact, this particular geometry we did create, with our CAD tool, but ultimately you could just directly import the G code, which is really exciting because someone has already invested quite a bit of effort to get the G code, to go through the slicer, to get it ready for print, and all of that information is literally the same information that we need to simulate that print process. So what we're trying to do is create, if you've heard the term, a digital twin, where our process up to the point of printing is a common, all the way up to the G code. And then we can either take that G code and go and keep it in the computer and simulate, or take that G code and go to the machine and actually print the part. So up until that, everything should be the same. But some of the items that we need for the thermal is, of course, as I mentioned, the melting temperature, right? So we're assuming that this material comes into the simulation right after it's been, right at the melting temperature, right as it solidifies, and then it's kind of cooling down to ambient. And then we have things like this thickness, right? So our layer thickness or deposition thickness, and the scan speed. And again, as a production house, you might think to yourself, I want to crank up that scan speed. Well, there's an optimization there. If you crank up the scan speed to try to print as quickly as possible, make a bunch of money, get it to your customer sooner, you are going to be putting a lot more heat into this print a lot faster. So, we use these tools to find out how fast can we go without going too fast and impacting the quality. We have a dwell time that we can add in between each layer, so that allows, before we bring in the next layer, allows the part to cool a little bit and get some of those residual stresses to kind of dissipate through the part so that we're not adding too much heat all at once. And then we've got a variety of different build and cool down conditions. So this particular model actually has 3 phases. We have a print phase or a build phase, we have a cool down phase, and then we actually have a removal phase. So we're able to actually remove the part from the bed and then find out how much it's going to boing, spring back, right? Because as it's sort of welded to the bed here, like any other welding process, the part's kind of stuck in its fixture, if you will, and then as soon as you release it, you always get a little bit of movement. So this model here has all 3 of those steps. You can see we've got a big gray bed here at the bottom. We're able to control what its temperature is and ultimately how it's going to be supported. You can see that we have a yellow, blue, orange, and green support, and we'll remove those supports during the separation process. So we've got this pre-solved in the sake of time, so we can take a look at the temperature. So this right here is the temperature profile, and this particular temperature profile, if you look at the graph down at the bottom, we have the total time frame here. So we start off with the first layer, and then we go all the way down to the cool down. So let me just hit play here, and we can watch this whole process. Start at the beginning. So what we're seeing here is layer by layer by layer, we are increasing and adding a material and adding temperature. And then ultimately after that, it goes all blue because we're cooling it down for the separation phase. So we have a thermal profile of every single layer, and we're here to predict how much that temperature and that heat energy is dissipating into the part and then into the environment of the build machine as well. So that's the thermal profile. So once we capture that and we understand what that thermal profile looks like, we feed that into a structural analysis. And that structural analysis gives us probably one of the most important things that we want, which is the deformation, right? How much is it going to deform? And in this case, as you can see, this is after the removal step. So again, towards the bottom of the screen, you'll notice we've got the build step, we've got the cool down step, and we have the removal step. And I'm just going to start at the beginning again and hit play. So we've got the build step, and then we've got the cool down step. So we've got very, very little deformation through the build because everything's all fixed in place. And then ultimately, as we remove it, we kind of see that, boing, the cantilevered part furthest away from the left is going to move a little bit. In this case, it moves up, 3.8 millimeters. So what we might do in real life is we might print this with our process, separate it from the build plate, and then put it into quality control and measure how much did it deform after it had been removed. And if it was 3.8 millimeters, then now we have a model that matches that. If it's a little more, a little bit less, then we've got ways to tweak this so that the model matches. So really, we only really need to print 1, maybe 2 parts, and then we have a simulation that can predict any parts that we might want to design in the future. And then finally, the last thing we want to look at, of course, is stress, because any structural or mechanical engineer or your customer, for example, will be very interested to know what are the residual stresses. Let me hit play here. What are the residual stresses inside of this part as we remove it, as we print it, and how can we reduce that? And so again, there's this optimization of I want to reduce my residual stresses in the part. I want to avoid a post-process heat treat if I can, but I also want to print it as fast as I can. So anytime, again, we have an optimization opportunity, then simulation is a fantastic way to predict that and to make the best parts possible. So I want to thank everyone for their time today. Hopefully this gave you a little bit of insight into some of the tools and simulation software that's out there. I wish you all the best of luck as you look at new tools and new processes. And if there's anything that we can do to help, please don't be afraid to reach out. And now I think we're going to open up the floor to some Q&A. So thank you so much.